Hello, George Romanic here. Welcome to Fundamentals of Weather and Climate playlist. Consider a parcel of air that we defined in the previous video, an imaginary volume of air. Then this imaginary volume of air, perhaps in this room, or in your room, or somewhere in the atmosphere, has temperature T, pressure P, and density ρ. These three variables are connected through the equation of state for an ideal gas that says that pressure is equal density times gas constant times temperature. Now, I would like to discuss a little bit this gas constant R. While we call it gas constant, it varies depending on the composition of the gas, namely composition of air in this parcel of air. What do I mean by that? Well, you know from my previous videos that this parcel of air has nitrogen N2, has oxygen O2, has argon in small amounts, and maybe some other gases like CO2, methane, and so on. But in addition to these gases, it can also have water vapor, H2O. Now, these gases, nitrogen, oxygen, argon, and so on, come in more or less fixed amount, particularly nitrogen and oxygen. It's 78% nitrogen, 21% oxygen, less than 1% argon, and so on. But water vapor is variable because water vapor can condense and become liquid water, or liquid water in the atmosphere can evaporate and become water vapor, as we discussed previously. So that means the amount of H2O, water vapor, varies in this parcel of air, or could vary, which means that this gas constant also varies, and that is not desirable. To address that issue, we know from my previous videos that these are called dry air, or dry air gases, whereas this is, as I just said, water vapor. So, from Dalton's law of partial pressures that we discussed previously, you know that total pressure in this parcel of air can be expressed as pressure of dry air, namely pressure that these gases exert, plus water vapor pressure. So consequently, I can write this equation for dry air, namely pressure of dry air is density of dry air times gas constant of dry air times temperature. Now, this gas constant of dry air is indeed constant. It has value of about 287 joules per kilogram per Kelvin. But similarly, we can write this equation of state for water vapor, that pressure of water vapor is density of water vapor times gas constant for water vapor times temperature T. This is also constant. 465, I think, joules per kilogram per Kelvin. You can double check online. Now, we also now, this is the beautiful part, we connect concepts from previous lectures. You remember the concept of virtual temperature. What is virtual temperature? Virtual temperature is temperature that dry air should have to have the same density as moist air at a given pressure. Because dry air is denser than moist air, that means dry air needs to have a little bit higher temperature to have the same density as a given volume of dry air that is at the same pressure as that moist air. Well, anyways, if you don't understand what I'm saying now, I have an entire video devoted to virtual temperature explaining this concept. Now, because this is fundamental playlist, as you know, I'm not deriving equations here. I'm doing it in advanced playlist. I can tell you that these three concepts can be combined in a rather beautiful way to write equation of state for moist air using dry air gas constant. In other words, we say that pressure of moist air is equal density of moist air. Now, not gas constant for moist air, but gas constant for dry air. But in that case, we are not using temperature, but we are using virtual temperature. And this is very, very used equation in atmospheric sciences, because we managed to use fixed constant that doesn't depend on the amount of water vapor in the air. Namely, it doesn't depend how moist or how humid this parcel of air is. It's a fixed constant, this value. But for the amount of moisture in the air, we use virtual temperature. And you know from my video on virtual temperature that it is equal temperature 1 plus 0.61 times mixing ratio, where mixing ratio is mass of water vapor divided by mass of dry air. I explained everything. So you can see if air is perfectly dry, mass of water vapor is 0, this collapses to 0. And then virtual temperature is equal actual temperature. That makes sense. Equation of state is beautiful because whether you want to use this one, this one, this one, or that one, it gives you a very simple algebraic equation that combines three very important quantities: temperature, pressure, and density. And you can now calculate a number of beautiful phenomena in the atmosphere or even in your room. Let me just give you an example where you can use it. If you have an oven, you are cooking pizza in your oven, and you know that temperature in the oven is 300 degrees Celsius. That's very hot oven indeed. And you know that air density in the oven is, I don't know, 1.2 kilograms per cubic meter. Well, then from here you can calculate what is the pressure in that oven. Simple algebraic equation. Or in any other case, if you know temperature and pressure in your room, you can calculate density. In fact, how we typically use this equation is the following. Pressure is easy to measure in the atmosphere. Temperature is easy to measure in the atmosphere. Density is extremely complicated to measure in the atmosphere. So whenever we have density in our equations, we tend to use equation of state. Rho is equal P divided by RD TV. And now, whenever density appears in some equation, we use this substitution to eliminate density in favor of pressure and temperature, which we can easily measure using our instruments. In the next video, we are going to discuss first principle of thermodynamics, or first law of thermodynamics. Thank you for watching. Please make sure to like and subscribe, leave a comment, share this video, and until next lecture, goodbye.